This video will give you an introduction to trigonometric functions. Trigonometry is a branch of mathematics that studies relationships involving lengths and angles of triangles. A trigonometric ratio is a ratio between the lengths of the legs of a right triangle. There are three basic trigonometric ratios, although there are more that you'll learn about when you take pre-calculus. They are sine, cosine, and tangent. The way that they are abbreviated, and you may have noticed these buttons on your calculator, it's going to look like sin, but when we say it, we need to make sure we say sine. Cosine is abbreviated with COS, and tangent is abbreviated with TAN. To help memorize the trigonometric ratios, I use the phrase SOHCAHTOA. S in SO stands for sine, and you'll notice I've got an X after sine that would represent the angle measure. So if you know the angle measure, you'll write the degree. If you don't know the angle measure, then you would just write the name of the angle. So sine X is equal to opposite over hypotenuse, hence SOH. CAH, C-A-H, is for cosine. Cosine of X equals adjacent over hypotenuse. And TOA, tangent, equals opposite over adjacent. So in our first example, we're just going to practice setting up the ratios. So we have sine A. What that means is that you're going to be looking at angle A when you're setting up these ratios. Okay. So sine, remember it's SOHCAHTOA. Sine is equal to the opposite leg over the hypotenuse. So from angle A, side A right here is the opposite, and the hypotenuse will always be C. Cosine of A means we are looking at the leg adjacent to angle A, which would be B, over the hypotenuse, which again would be C. Tangent, TOA, means the opposite from angle A over the adjacent leg to angle A. So if we look at angle A, the opposite is side A, and the adjacent is side B. Now we're going to do the same thing, but we're going to do it in reference to angle B. So sine B means our reference angle is B. To do sine, we need to do opposite over hypotenuse. So the opposite side from angle B is side B. And the hypotenuse, again, is C. When we move on to cosine, that is the adjacent leg to B, which is side A, over the hypotenuse, again, side C. And finally, tangent, TOA, is opposite over adjacent. So the opposite side from angle B is side B, and the adjacent leg would be side A. Often in trig, we name the sides. So for instance, side AB, in previous units, we've just called that segment AB. But because that side, which happens to be the hypotenuse, is opposite from angle C, we can call that side C as well. And the side would be a lowercase c. Or the side opposite from angle A can be called side A or segment BC, and then the side opposite angle B can be side B or segment AC. So you're asked if you can use angle C, which is the right angle in this picture, for a trigonometric ratio. So let's think about if we tried to do that. If we tried to use side C and we tried to do sine C, Sine means opposite over the hypotenuse. Well, opposite from C is the hypotenuse. So the opposite and the hypotenuse would be the same thing, which doesn't make sense. Or if we tried to do cosine, which is adjacent over hypotenuse, there are two adjacent legs, A and B, so that doesn't make sense. So you will never do trigonometric ratios from your 90-degree angle. It will be from one of the non-90-degree angles, so one of the acute angles. So can you use angle C for trigonometric ratios? No. And there's a couple different ways that you could explain it, but you could say the opposite is the hypotenuse. I'm just going to kind of abbreviate for space. And there are two adjacent legs. Two adjacent legs. Something really important to know with trig ratios is that the sine and the cosine of complementary angles are equal. So I don't know if you noticed it in the last slide, but I'll point it out as we do example 2 and example 3. But in our last slide, the sine of angle A was equivalent to the cosine of angle B. And likewise, the cosine of angle A was equivalent to the sine of angle B. So the sine and cosine of your opposite angles are going to always be equal. And again, I'll point that out in our next two examples so you can see exactly what I'm talking about. So in example 2, we have a right triangle. We have all three sides. Should you only have two of the sides, then you would want to use the Pythagorean theorem to find the missing side. So we're going to do our ratios. If your ratios simplify, you want to make sure that you simplify your ratios. So if you get something like 8/10, you would want to simplify that to 4/5. Okay, so we're going to again refer to SOHCAHTOA. And just as a reference point, the S means sine, and then the O is opposite, and H is hypotenuse. C is for cosine, the A is for adjacent, H is for hypotenuse, and I think I just spelled that wrong. T in TOA is for tangent, and that's opposite over adjacent. All right, so sine of A means we're going to look at angle A. And when we do the sine, we're going to do opposite from angle A, which is 5, and then over the hypotenuse, which is 13. All right, then we're going to do cosine of angle A. Cosine means adjacent over hypotenuse, so make sure you use the adjacent leg, because some people would argue that 13 is adjacent, and yes, it is adjacent, but it is the hypotenuse and it's not a leg, so you want to make sure you're using the leg. So from angle A, 12 is adjacent and 13 is the hypotenuse, so the ratio for cosine A would be 12/13. And then finally, tangent for angle A means opposite over adjacent. The side opposite from angle A is 5, and the adjacent is 12. Make sure you do not use the hypotenuse in tangent. So now we're going to do the same thing from the other angle, which is angle C. Sine C means opposite from angle C, which is 12. Over the hypotenuse, which is 13. Cosine C means adjacent to angle C, which would be 5, over the hypotenuse, which is 13. And tangent C would mean opposite leg from C, which is 12, and then over the adjacent, which is 5. And to refer back to the slide, the previous slide that we just did, sine A and cosine C are the same. Cosine A and sine C are the same. Because when you switch your angles, your opposite becomes your adjacent and your adjacent becomes your opposite. And so that's why it's switching. The hypotenuse remains the same no matter which angle you're talking about. And the other thing you might notice is that tangent of A and tangent of C are reciprocals. And again, that's because your opposite and adjacent switch spots when you change your angle. Now, these ratios right now may not really make sense why we're doing these ratios, like what's the purpose of them, but in the upcoming lessons we're going to be using this idea to help us find a missing side or potentially a missing angle. So right now we don't have any missing sides, but we can use these ratios to help us find the angle measure of angle A and the angle measure of angle C. All right, let's try one more. We're doing the same thing. We're changing our angle names to C and T instead of A, B, and C. We're not going to do these ratios with angle A because angle A is the 90-degree angle and we can't set up our trig ratios with our 90-degree angle. So what you'll notice here is that we are missing one of our sides of our triangle. We're actually missing the leg. So I am going to start by finding the length of segment AT first. So in order to do that, since it's a right triangle and we have two sides, I'm going to use the Pythagorean theorem. So we're going to do x squared plus 7 squared equals 25 squared. We are looking for a leg, that's why I put it in the position that it's in. So 7 squared is 49. 25 squared is 625. I'm going to subtract 49 from both sides. And that gives me x squared equals 576. And finally, we're going to take the square root of both sides, and x is going to actually equal 24. It's going to be an exact value. This is one of our Pythagorean triples that I mentioned. So now if we go to do sine of C, we're going to focus on angle C. Sine is opposite over hypotenuse. So from angle C, the opposite leg is 24 and the hypotenuse is 25. You always want to look at these fractions and see if they reduce. 24 over 25 does not. Okay. Cosine of C, cosine is adjacent over hypotenuse. So from angle C, 7 is the adjacent leg, and the hypotenuse is still 25. And then finally, for tangent of C, that's opposite over adjacent, TOA. From angle C, the opposite leg is 24, and the adjacent leg is 7. That does not simplify, so we don't need to simplify anything. You don't need to turn it to a decimal. You don't need to turn it to a fraction or a mixed number. Just leave it as an improper fraction if it is one, and don't change these to decimals. So now we're going to do the same thing from sine t. Now, if you use the rule that the sine and cosine of your complementary angles are equivalent, you can actually just go ahead and do cosine t because that's going to be the same thing as sine c. But it's okay if you don't see that because you can just look at t and the adjacent leg is 24 and the hypotenuse is 25, so 24 over 25. Sine t is going to be equivalent to cosine c, so it's going to be 7 over 25. Again, if you don't recognize that, look at angle t. The opposite leg to t is 7, and the hypotenuse is 25. And then finally, tangent. You can do the reciprocal of tangent c to get tangent t. Or you can look at angle T and write the opposite leg, which is 7, over the adjacent leg, which is 24. Again, the ratios, leave them as simplified fractions. Don't turn them to mixed numbers. Don't turn them to decimals. These will be really important to help us find missing sides and lengths.